part of this stuff would be finding all the zeros, you know, with giving your tails and stuff like that. So let's get into how you graph these. And what I want to do here is start with something very simple. And I want to talk about how you would graph the following polynomial. Now, once again, I'm not giving you graph paper. I'm not setting any of that up. There's no reason for us to have graphs or graph paper. We're doing graphing via some very simple things. We're going to graph and plot our zeros, maybe find a y-intercept if we need to, and place the tails on. Now, remember when we're talking about the tails of our functions, we're talking about the funky dances. Those things. Exactly. So we're talking about stuff like that. Now, when I'm looking at this function, I have f of x is x minus 2, x plus 4. What's the degree of this function going to be? It's 2. It's a second degree polynomial. Is a second degree polynomial, is the leading term going to be positive or negative? So what are your tails going to do? Going to go up. Tails are going to be up on this one. Now, this is also written in what we call, if you remember, intercept form. Remember that? Yes. No. What's that? If you FOILed this out, what would your leading term coefficient be? Where do you see it? 2. X squared. So it's positive, right? That's why. So these are giving you your zeros. You agree? Yeah. You have zeros at -4 and positive 2. We know that our tails would be going, excuse me, our tails would be pointing up, so I know it's going to be coming and doing something like this. Now, one of the other points that I could plot on here to make my life pretty easy would be my y-intercept. Remember how we had talked in the past that f of x is kind of synonymous with y equals? Now, if y is, you want to find your y-intercept, what is your value of x going to have? 0. How do you find that then? Substitute in. So to find my y-intercept, I know that y is going to equal 0 minus 2 times 0 plus 4. What's your y-intercept? -8. Can you plot that? And that's what you're looking at being able to do. When we're looking at these polynomials, we're looking at graphing and plotting it via zeros. A y-intercept, you know, if it's close enough by. What's that? I substituted 0 for x. Okay. Now, the other thing is, now this being a quadratic, because it's an x squared term, we know that the vertex is a what? Is the vertex a maximum or a minimum? It's a minimum. Why do we know it's minimum? So we know that this point down here would be the minimum. Now, the other thing I want to point out to you, is that since this is a second degree polynomial, how many times does the graph change direction? Once. Since this is a second degree polynomial, you have one direction change. Okay. When it's a second degree, that place where it changes direction is at its vertex. So we would call that either its maximum or its minimum. In this case, it's a minimum. All right. In your calculator, you could find that. Do you remember how? Yeah. Yeah, the whatever it's called thingy. I'm surprised they actually sat still for 30 seconds. That's Lake Superior, in case you were wondering. We're way up there.
What state?
Minnesota. Minnesota doesn't have it.
Oh wait, no, sorry, wrong one. Wrong state I'm talking about.
We were in the UP of Michigan last summer.
Okay,
This
I
summer
was
we went up.
there a couple of summers.
Yeah, we went up there. We were up in the UP 2 summers ago. Our function was what? X minus 2x plus 4. You can put it in your calculator exactly like that with your parentheses, and it works just fine. Was X, was it, or was it X? Did I have it right?
Yeah.
Okay, for some reason I thought I was wrong. So when I go look at the graph, it looks something similar like that. Remember, your calculator will find that minimum value for you. What buttons do you press?
Is it like alpha,
No?
alpha y squared?
No? Second, calculate. Second, trace.
Oh, and then you go to the minimum.
And then you go to the minimum. And why do you have to go to, excuse me, why do you have to go to the minimum?
Because it is a
Because you
minimum.
want the minimum, not the maximum, or the zero, or the value, or the intercept.
Boy, you might be reading the other half sheet of paper.
Oh, yay!
What?
Then I can write the rest of my name.
Oh.
So in this case here, it's asking you for your left and your right columns. Remember what you have to do? You're moving stuff around. Oh, now look where my cursor is here. My cursor is not to the, I have to be to the left of where I think it's going to occur. So my minimum's occurring at -1 and -9. You okay with that? Even though you have a little bit of rounding errors in there, that's calculated it out for you. So on your work then, you would know that your minimum is occurring at -1 and -9. Notice you did not need to try and do any of that by hand. The worst that you had to do was find zeros in your x-intercept. To find a minimum, what we're going to be doing is using our calculators. And this process to find a minimum does not change when we go into a cubic or a quartic style polynomial, 3rd or 4th degree. It all works the same. So let me show you. In this case, I have a new function. F of x is 1/4 times the quantity x plus 2, and then x minus 1 quantity squared. Now, I wrote up on there already a little bit of a hint that it's going to be a 3rd degree polynomial. Does everybody agree that it's going to be 3rd degree?
Yes.
Why is it a 3rd degree?
Because it's trace.
Because there's trace x's. Okay, I'll give you that.
Oh.
No, there's 3 of them.
Oh, okay.
Sacre bleu.
What?
Definitely.
Spanish.
Totally.
Nod and smile. Which now, since you have a 3rd degree polynomial, that means you can have at most, you can have at most 2 changes of direction. Is it possible you only have 1 change of direction?
Yes.
It is,
How?
because well, sometimes you'll have functions that have imaginary solutions. And when you have a function that has imaginary solutions, it is completely possible you might not have a change of direction for that. Because when you graph things in the real world, imaginaries don't show. Okay? Yeah.
Is the ball 5 cents?
It is. Okay. So in this case here, I put a big giant hint of plotting zeros. My zeros of this function are at -2 and +1. How many times? Twice. Here's the thing. When you have a 0 that is duplicated, that means there's going to be some parabola hook that happens on it. Whether it's up at that spot or down at that spot. It's going to be either one of those.
Why did you make it like right there but not
Because remember when you did this? If you FOILed that out, you get x squared minus 2x plus 1. Do you agree? That means that your zeros, when you factored it, were at just at +1. The curve of that quadratic came down and touched the x-axis in only one spot. It didn't go through it twice. Remember that when you're talking about zeros here, you have the possibility of having up to 2 zeros, but in this case, you only have one that's just duplicated. That can occur in these things as well. That's why they leave them as squared. So what's happening here is that it could be hitting this thing coming up like a cup like that, or it's possible it could be, depending upon what the tails are, it could be coming up on that direction. So what we do is, we know that first term is going to be what? Positive or negative? If it's positive, it's a third degree polynomial, what direction are your tails? Well, like that, right? So that means it's coming up this way.
How do you know it's not the other way? Because we're not positive.
Remember the rule?
Oh.
So what's happening here is that my curve is just going to touch that spot at one time.
Yeah.
So you have one direction, two directions, and you're gone. So you have got your two directional changes for a third degree polynomial, even though it appears as though it's only touching the x-axis with two different zeros, one of them is duplicated. So it still has 3 zeros. So the fundamental theorem of algebra saying that you have a third degree polynomial, you have 3 zeros, still holds. Yes?
But I guess you're making like an ugly stuff on that one, like you're also making a darn. Never mind.
And I know where you're going with that. You're in. Now, the only other spot that we can figure out here by hand is a y-intercept, correct? The y-intercept is when x is equal to what?
0.
0. So if I wanted to figure out what this ordered pair is, all I do is take 1/4, 0 plus 2, 0 minus 1, quantity squared. What's 0 minus 1?
Negative 1.
What's negative 1 squared?
1.
What's 0 plus 2?
2.
What's 2 times 1?
2.
What's a fourth of 2?
Wow.
point something.
So that y-intercept is at 0 and 1/2. Okay? It crosses the y-axis at 0 and 1/2. Now, Izzy, what you were, I think, starting to freaky a little bit about is what's happening here and here. In this graph, you have both a maximum and a minimum. Everybody see that?
Yes.
Now, instead of calling it a maximum and a minimum, in this location, this is called a local max, because it's the high point, and it's measurable. We're going to be able to measure what that value is because the curve changes directions there. I can't measure maximal amounts on my tails because they're going through infinity. There's no maximum value on the tails here. I can also find this value here. This value is going to be a what?
Local min.
Localized minimum.
Wait, don't we know what it is?
We do. In this case, we know what that local minimum is. What is that local minimum?
0.
Or was it 0, 1 or 1, 0? 1, 0. I know that localized minimum here is at 1 and 0. This localized maximum, I don't know what it is, but what can I use to find it?
Well,
You gotta get over
Your calculator. I can use my calculator to find that. All I have to do is put this function into my table.
wouldn't they be the same distance away from each other?
Not necessarily. When you get into the upper degree polynomials, they're not necessarily symmetric. I forgot what that was called. So when I go into my y equals here, instead of putting in the 1/4, can I put 0.25? Does it change anything? It's just quicker to type in. I put 0.25, x plus 2, x minus 1, 20 squared, and I go to my graph. Everybody see that? Okay. Now all I have to do is just find my maximum at that one value, that localized maximum. Second, calculate. Which one is it?
Maximum.
You can put your other half of your name on.
Really?
Yes.
Okay, wait, but I need a whole new, I need a half.
You have to rip another half off. You can't do it.
Yeah, I know.
And you know if it's not exact, she's just going to go crazy.
Whoa.
You can make it mad. So my localized maximum, it just so happens, of course, not to be it. It happens to be at negative 1 and 1.
How
I
do
messed
you do
up.
that?
Using the calculator to do the work for you. Not bad? Do that one then, please. Plot it, zeros, y-intercept, and localized maximums, please. All right, let's check and see where we're at, because I want to do one other quick thing with you guys here today. Does everybody agree you have zeros at plus minus 3 and negative 4?
Yes.
Okay. So we have zeros at plus and minus 3, negative 4. My tails tell me that I have a third degree polynomial that's negative coefficients. So which direction are we going? So I know I have to be doing this. There's something going on. I don't know how high up that goes or anything like that.
I'm confused on how
Is
you
it way up there? Okay.
How do you know where the graph is going again?
I got negative.
You're using your what's happening at the tails. You're looking at what's happening as x is approaching infinity, as y is approaching infinity, or as. Think of it this way: if it's an even function, it always is going to follow the pattern of a quadratic. If it's an odd function, it always follows the pattern of slope. This is an odd function. Your slope is negative, because negative 2 is your coefficient. Negative slope goes down and right.
It's quadratic.
Quadratic goes up or down. Just positive or negative. Okay. So now what I have to figure out was my localized maximums, localized minimums, and a y-intercept. When you do the y-intercept here, you're substituting 0 for x. You agree? So you have negative 2 times negative 9 times 4, so that's 72. So it's at 0 and 72.
I get it now.
Okay? Localized maximums and minimums, are you guys okay with just plotting pressing buttons on your calculator, or do I need to continue with that?
No.
No.
Wait,
No, I don't need to, or no, you're not okay?
No, don't do it.
Okay. Those should be pretty easy to find. Now, the last little bit of these things I want to do with you guys is to get you to write the equation given plotted out ordered pairs. Oh, where is that?
5, 7.
I want to write the function. I want to write the cubic function given ordered pairs. So my ordered pairs are negative 3, 0, 0, negative 15, 2 and 0, 5 and 0. I want to write out the function. I want to know what f of x is equal. Okay? Excuse me. I want to figure out what f of x is going to equal. Now, when you're given these things, you will always be given certain number of zeros and usually another set of ordered pairs. Because what happens is these functions are always going to follow the same pattern. Some value a, doesn't matter what it is. In this case, it's telling me I'm going to write a cubic function, so I'm going to have 3 zeros. Everybody okay with that?
Yeah.
According to my graph, my zeros are at negative 3, 2, and 5. Also, I can look at that with my ordered pairs. If my zeros are at negative 3, 2, and 5, what are my 3 terms?
X plus 3, X minus 2, X minus 5.
Everybody okay with that?
Yeah.
So now we have to figure out what the value of a is. So here's what I want you to think. What is another word for f of x? Y. So don't I already have y equals a, x plus 3, x minus 2, x minus 5?
Yes.
Yep. Then what does x equal?
X equals 0.
I don't know what it is. I haven't done it yet.
Wait, I think it's,
So what's happening here is I'm going to use that last set of ordered pairs to substitute in for y and x. So in this case, my y value is negative 15. That'll equal a times 0 plus 3, 0 minus 2, and 0 minus 5. You okay with that?
Yeah.
So what's 3 times negative 2 times negative 5?
Oh, 30.
Negative 30.
No positive.
It's positive 30. Try that.
So what's the value of a?
Negative half.
Half. And doesn't that match the way the graph is going? If it's a cubic function, notice how the graph tails are pointing down like a negative slope? So now all you have left to do is take this value of a and substitute there. And you're ready to rock. It's a very, very easy process. Yes, Izzy?
Why did you not use the zero to reverse this?
Because I wanted to show you where we were going with it. I wanted to show you that f of x was a times the 3 zeros. And then how do you get to that value of a? Well, you substitute in that x and y, that leftover x and y. That's all. If you want to jump right into that right off the bat, that's fine, Izzy. I have no problem with that. And then just write out your function at the end. Works just the same. That's fair.
Okay, so if it was like 2 negative 15, would you just put 2 in place
Yep.
of 0?
Yep, that's all it is. Because it's going to give you your zeros and it's another ordered pair. You just substitute in that other ordered pairing. Okay? This is a very common way of writing out functions. We're going to do it with polynomials. Next week, we're going to go back and do it again with quadratics and things too. It's very, very easy when we do some of the modeling stuff. Yeah, I just did that one. How much time we have here?
6 minutes, 7 minutes.
All right, do this one. Write the function, please. Write the function given. This is going to be a cubic again. Be a third-degree polynomial. Go ahead and write the function out. See if you can do that. One of the things that I would do as I get started on these things is just to do a quick little plot of what they're giving me. Okay, they're giving me something like that. So what are my zeros then? My zeros are at negative 1, negative 2, and 0. Okay. So if I start to write that out, I got f of x is going to equal a x plus 1, x plus 2, and x. Can I write it as x plus 0 for right now, or whatever you want? We'll leave it like that. So now, all I have to do is substitute in that value of x and y to figure out a. So negative 3 is going to equal a, 1 plus 1, 1 plus 2, times 1. So what's 1 plus 1? 2. What's 1 plus 2?
3.
What's 2 times 3?
6.
Times 1.
6.
Divided by negative 3 equals negative 1/2.
Negative 3.
6 divided, yes, negative 3 divided by 6.
Oh, whatever. That's fine.
Close only counts in horseshoes and hand grenades.
Oh.
All right.
Oh.
There's your value back. Make sense? It works the same if you have a 4th degree polynomial, 5th degree polynomial. You just have more to multiply out. That's all. And then I'm assuming you can multiply, you can write that out. You don't have to multiply out the function. You can leave it in terms of the intercept form like this with the a value there. Let me give you a couple of these to try. It's mixed between both 6.8 and 6.9 here. So let's see, section 6.8 is the page 376.
You mean like the
Yeah, local max, local mins, things like that. And then the 6.9 stuff is page 383, 19 through 22. Oh. Okay. What is it, 7, 8 problems
Probably.
maybe? Shouldn't be that bad. We'll talk about how we use our graphing calculators for the funky polynomials tomorrow. And then I'll give you a couple of the word problems over the weekend, as well as some review things. Okay? Yeah.